Today we'll be going over formulas of compounds, specifically looking at empirical formulas versus molecular formulas. So first we'll be talking about empirical formulas. So yesterday we looked at getting percent compositions based on a formula, right, for a chemical. Well, first I want you to think about it. So if I have, Halloween, right? And I'm going through and I'm looking at my Halloween candy, and if I have 20 M&Ms and 80 Starbursts, and I want to know, so I know this sounds like, wait, where are we going with this? Don't worry, I'm just trying to draw a connection from what you know outside of chemistry to hopefully help you understand how we go about this process for figuring out empirical formulas in chemistry. So if I have 20 M&Ms and 80 Starbursts, and I want to know what is the ratio between my M&Ms and Starbursts. Okay, so if you take a look at that, well, you say, oh, for every one M&M I have, I must have 4 Starbursts. Well, how did you figure that out? Well, you took the two numbers and you said, oh, well, I've got 80 Starbursts. If I divide by my smaller of the two numbers, which is the 20, I say that I have 4 Starbursts. And I do the same thing for my M&Ms. I've got my 20 divided by my 20, which gives me 1 M&M. Oh, well then that means that I must have 4 Starbursts. Oops, there's an R in Starburst. For every 1 M&M. Or another way you can write that is it's a 4-to-1 ratio, right? Of Starbursts to M&Ms. Okay, so when we're doing empirical formulas, we're going to be doing something very similar. We need to figure out how many of each of those we have. All right, so if I were to tell you, so this is going to be doing empirical formulas from percent composition. So yesterday we figured out how to calculate the percent composition. Well, now we're going to do empirical formulas from it. So let's say that I told you that you've got 48.2 grams of carbon, you've got 12.4 grams of hydrogen, and you've got 32.6 grams of oxygen in a molecule. This is all in one molecule. And I ask you, okay, what is the empirical formula? Well, the first thing I need to do, take a look at what we did up here with the Starbursts and the M&Ms. We had specific numbers. These are counted numbers. Well, grams are based on mass, not on counted numbers, but moles are based on counted numbers. So if we convert this over to moles, then we can kind of look at it the same way we did with the candies. So I'm going to convert this over to moles. So for every 1 mole, for our for our carbon, looking at the next problem, which does have calcium, for our carbon, we've got 12.01 grams per mole. So for every 1 mole, I've got 12.01 grams. Remember, this needs to go on the bottom because we need these grams to cancel. All right, this will give us 4.01 moles of carbon. I'm going to do the same thing for my hydrogen. So for every 1 mole of hydrogen, if I look up here, I've got 1.008 grams of hydrogen. Okay, this gets rid of my grams. So this will give me 12.3 moles of hydrogen. Okay. Next one, we're going to do oxygen. For every 1 mole of oxygen, it will be 16.00 grams. 16.00 grams. So cross out those grams, cancel out. So this will give me 2.04 moles of oxygen. So just like what we did before with the candies, we need to look for the smallest number. So which one is the smallest number? In this case, I've got 4, 12, and 2, so that 2.04 moles is our smallest number. So we are going to divide by 2.04 moles for all. That way we can get a ratio, just like we did with those candies. Okay, so for the carbon, I've got 4.01 moles of carbon. I'm going to divide by that 2.04 moles. Okay, this will leave me with a ratio number of 1.97 for carbon. Moving on to the next one, we've got the hydrogen. That was 12.3 moles of hydrogen is what we calculated, divided by our smallest number, which is the 2.04 moles. This will give us a number of 6.03 for hydrogen. Alrighty, oxygen is going to be that 2.04 moles of oxygen divided by the 2.04 moles, because it was the smallest one, right? This one's going to be 1 oxygen. One of these, whenever you do this, check yourself. One of these should end up being exactly 1. If it's not, oops, you might not have kept it consistent, because remember, we always have to divide by the same thing, and it comes from one of them, right? All right, now, when you look at empirical formulas, do you ever have a decimal for them? No, you don't normally have 1.5 of a carbon. No, you have 2 carbons or 1 carbon, right? So what you need to do next is you need to round to a whole number. So this one will go to 2 carbons. This one will go to 6 hydrogens. Well, and this one doesn't change, right? This is still going to be 1 oxygen. Now, to write the empirical formula for that, remember, if I write it out, I've got carbon, I've got 2 of those. Hydrogen, I've got 6 of those. And my oxygen, I've got just 1 of those. Look at this. This is our empirical formula. Okay, so I said percent, right? So this is if you do it if you're given grams, but there's an extra step. So first of all, let's write down some steps. Steps for percent composition to empirical formula. All right, so the first step is, which we kind of skipped in this first example, and I'll do one with it, so don't you worry, okay, is you are going to convert percentages to grams by assuming that you have 100 grams. And like I said, I'll show you in this next example what I'm talking about. Okay, the next thing will be to convert those grams to moles, because remember, moles is kind of like a dozen. It's a multiplier by the number of things we're dealing with. We're talking about the number of carbons or the number of hydrogens or oxygens in this last example, right? So to get ratios, we need to get it into the number of them that we have. So we need to convert grams to moles. Then, once we have that, you're going to divide, and this is the step I see students skipping the most, so don't forget. Divide all by the smallest number of moles, right? This will get you your ratio. Okay, then you're going to round to nearest whole number. There is a caveat to this, okay? If if you have well, maybe not necessarily 0, if you have something 0.5, a 2.5, a 3.5, or what have you, then you will have to double all your numbers. And I'll show you this in this next example. Okay. Alrighty, and then once you have whole numbers, then you're going to write your empirical formula. Okay, so let's take a look at another example. Let's say that you have I want to make this a percentage thing. I was about to not make it a percentage thing. Okay. And I need it to add up to 100, so give me one quick second to convert my numbers correctly. All right, so for this first one, I tell you that you've got 26.6% potassium. And 26.6% potassium, you've got 35.3% chromium, and then you have 38, oops, didn't write for some reason, 0.0% oxygen. And I ask, what is the empirical formula? So the first thing, remember I said that you assume 100 grams. Well, if we assume 100 grams, well, that means that I've got 26.6 grams of potassium. And I've got 35.3 grams of chromium. And then I've got 38.0 grams of oxygen. Okay, remember our first step is to then convert. So I converted it from percentages to grams. So that step isn't quite as complicated as you would assume, right? It's the same thing, we're just changing the percentages over to grams. That's the wonderful thing about assuming that we have a 100-gram sample. Okay, now we need to convert those grams over to moles. So I'm going to set up my ratio. I'm going to go up and I'm going to find potassium on my periodic table. So potassium's right here. It's 39.10. So 39.10 grams per mole. Remember, we can inverse that to get rid of our grams. Okay, putting that into your calculator, you will get, 0.68 moles of potassium. Okay, now let's take a look at chromium. Okay, so chromium, let's go up to our periodic table. Uh-oh, give it a second, hopefully it'll come back. Oh, dang it, okay. Going back in, here we go. Chromium is right here. It's 52.00. So going back down here, we've got 52.00 grams for each mole. Our grams cancel, leaving us with just moles, which is what we want. Okay, plugging that in, you should get 0.6788 moles of chromium. Next, we're going to convert oxygen. I'm just going to pull this because we just looked at it a minute ago. You got 16 grams per mole for oxygen. Okay, so this will give us 2.375 moles of oxygen. Okay, now we got everything in moles. We have to figure out which one's the smallest. So we've got 0.68, 0.788 and 2.375. So I would call this one our smallest number. So now we're going to divide everything by our smallest number. So we're going to start with our potassium. We've got our 0.68 moles of potassium. We're going to divide it by our smallest number, which is the 0.6788 moles. Our moles cancel. So then this gives us, it's going to be pretty close to 1.00. We'll just stick with that many sig figs for now, of potassium. So this is just basically 1. Chromium, we're going to do the same thing. We're going to do 0.6788 moles of chromium divided by our smallest number, which happens to be the chromium, so it should end up being exactly 1. And then our last one is our oxygen. Our oxygen is the 2.375 moles of oxygen divided by our smallest number, which was the 0.6788 moles. Okay, 2.375 divided by 0.6788 will give me 3.498 for oxygen. Okay, looking at this, this is basically like 0.5. Because it's 0.5, I need to multiply. So we've got a 0.5, therefore multiply all by 2. Okay, so then this becomes, well actually here we'll put it down under here. So potassium, instead of 1, we're going to have 2 potassiums. For the chromium, instead of the 1, we're going to have 2 chromiums. And then the 0.5, right, so we've got essentially 3.4988. We're going to multiply that by 2. So this will give me 6.9976, and that rounds to 7 for our oxygen. Now we can write our empirical formula. Okay, so it's going to be potassium, I've got 2 of them. Our chromium, I've got 2 of them. And our oxygen, we've got 7 of them. This is our empirical formula. Now, empirical formulas are excellent, and we love being able to find them. But what we have found is that the empirical formula is not always a good representation of our molecule. It tells us the ratio, but sometimes we need more information. So let's just do a quick table to show that. So I've got a few different chemicals here. So I've got formaldehyde, which hopefully you know is actually quite toxic and is used to fix things, so that way it doesn't, it's used to be used a lot, injected into different samples for dissecting and stuff. We've moved over to a new thing now, but it's because it's dangerous, right? So we've moved over to a new chemical that has the same properties for maintaining and preventing something from deteriorating so you can dissect it later. We now use something else, but formaldehyde's a good example. So formaldehyde, I'm gonna make a table actually really quickly. All right, so we're gonna look at its molecular formula. So its molecular formula is CH2O. Okay, it looks like this, in case you're curious. This isn't important, but I think it's always interesting to see how these molecules look. Okay. So its empirical formula is the most simplistic ratio. Apparently won't let me write the A. I'll try doing that again here in a sec. Okay, it is the most simplistic ratio. You can't get more simple than that, right? There we go. Now I can write the A. So that's formaldehyde. Okay, now let's take a look at acetic acid. Alrighty, acetic acid is C2H4O2. And for those of you who are curious, the structure is you have this methyl group over here, attached to another carbon, double bonded to an oxygen, and an OH group. Okay, acetic acid, well, think about the most simplistic ratio here is CH2O, right? You can divide those all by 2. That would be our empirical formula. Okay, let's move on and look at lactic acid now. So acetic acid, that is in vinegar. Okay, acetic acid is what makes vinegar have that lovely vinegary taste. Lactic acid, which is what builds up, or I guess now they're debating this, but this is what they told me when I was growing up. It's what builds up in your muscles that makes you sore. So we went from something that's formaldehyde, that's really dangerous, to acetic acid, which is something that we eat, to lactic acid, which is something that we produce after we work out really hard. All right, so it has C3H6O3, and it looks like this. Again, just for those of you who are curious on what the molecule looks like. We've got this OH group here. And then we still have this double bond to the oxygen. Okay, this, in its most simplistic ratio for the empirical formula, is still CH2O. Well, these are all super different. Formaldehyde's dangerous to us. Acetic acid, we eat. It is vinegar. Lactic acid, our body produces. They have very different molecular formulas, but the empirical formula is the same. Okay, so the empirical formula is going to be the most simplistic ratio between atoms. Right? The empirical formula just went down to CH2O for all of these. The molecular formula, so let's change over. So the molecular formula, I'm going to give it to you as kind of an equation. It's going to be your empirical formula multiplied by some n, right? We multiplied each of these numbers, how many carbons you have, how many hydrogens you have, how many oxygens you have, by some number. So if you look at acetic acid, our n that we would multiply by would be 2, right? Lactic acid, the n we multiplied by was 3, because I've got 3 carbons, 2 times 3 give me 6 hydrogens, and 3 oxygens. So that's what this molecular formula means. All right, so to find the n is going to be equal to our molar mass divided by the empirical formula mass. Okay, so let's take a look at that. So if I told you, so example, all right, so if I've got 71.65% chlorine, 24.27% carbon, and 4.07% hydrogen with a molar mass of 98.96 grams per mole. What is the molecular formula? Okay, so the first step you're going to need to do for this is you're going to have to find the empirical formula first. Okay, we're looking for molecular, but we're interested in empirical to start with because we need it to find the molecular. So the empirical formula, just like we were doing before, we're going to first convert these 2 grams, assuming 100%. So we can say 100 grams. If we assume 100 grams, we can say 71.65 grams of chlorine, 24.27 grams of carbon, and 4.07 grams of hydrogen. Next, we want to convert these over to moles. So for every 1 mole of chlorine, if I go up to my periodic table, we'll give it a second to pull it up. Hopefully it'll come up. Oh, technology. Here it goes. Okay. My chlorine is a halide. It's over here. It's 35.45. Okay, and while I'm up here, so we don't have to deal with that, carbon is the 12.01, and hydrogen's our third one. That's the 1.08. So we can write these all down. Okay, so, whoops, too far. All right, chlorine we said was 35.45 grams. And I'm just going to write the other ones down before we forget. We said that carbon was 12.01 grams and hydrogen is going to be 1.00 grams. Okay, sticking all of these into your calculator, you end up with 2.02 moles of chlorine, 2.02 moles of carbon, and 4.0. Why won't it write the 4? There it goes, 4.0 moles of hydrogen. Remember, we look for the smallest. We'll leave both the smallest, right? So 2.02 is going to be our smallest number. We divide by our smallest number. So for the chlorine, we say 2.02 moles of chlorine divided by our 2.02 moles, which will give us just 1 chlorine. For the carbon, we've got again 2.02 moles of carbon divided by our 2.02 moles. This will just give us 1 carbon. And our last one is hydrogen. So 4.04 moles of hydrogen divided by our 2.02 moles. This will give us 2 hydrogens. Okay, so looking at this, I can write our CH2Cl. This is our empirical formula, but we were not looking for empirical, we were looking for molecular. So we need to take it one more step now to find the molecular formula. We are going to, remember I said it was N equals your molar mass divided by your empirical mass. Well, molar mass, we gave it to you in the problem statement. Hopefully it's in your notes because it has disappeared from here. I said in the statement molar mass of 98.96 grams per mole divided by our empirical formula's mass. We have to add that up. So we have 12.01 grams per mole because the the atomic mass of carbon is 12.01 plus 2 times the atomic mass, if you look it up in the periodic table, is 1.008 grams per mole for your hydrogen, and your chlorine is going to be 35.45 grams per mole. You know you've been doing this too long when you have these all memorized. Okay, these all add up to grams per mole, so our grams per mole cancel out, which is good. If you plug this into your calculator, again, remember to put parentheses in your calculator for everything in the bottom, so it maintains it in the bottom. Our N is going to be equal to 2. So we take our CH2Cl from before and say 2. Now we have C2H4Cl2, and this is our molecular formula. All right, that's what I got for you today. Time to go practice.